We start this set of videos looking at the electrical properties of material. In particular, we're going to be dealing with classical types of materials like metals in these series of videos. We're going to start with the definition of current. The definition of current is the rate in which charge flows across a surface. So I is defined to be dq dt. So let us take a look at the surface here. We'll start at some place. We'll call this area right here. This is our surface. And if we're sitting here, we can count charge that passes through that surface in much the same way a person could count cars at an intersection. So you could have a car go this way. You also might have a car, in this case, our little car is this little positive charge going the other way. And if I define this to be a positive direction, then this one is a negative. So if one car goes that way, but another car goes this way, the net effect has been that there's no net flow of cars. It's a little more complicated, though, with charges than it is with cars, because you can have both positive charges moving and negative charges. And in motion of a negative charge, if a negative charge moves from one place to another, it leaves behind positive charge because charge is neither created nor destroyed. You can't just create a negative charge, you can only move it. So if you leave a negative charge leaves an area, it leaves the area from which it came more positive than it was before. Let's try to show that in this next couple of set of diagrams. And note this important fact that we're going to define the direction of positive current flow as the direction that positive charge flows, regardless of what is the actual charge of the particle that is moving. So here we see positive charges and they're moving this direction. The current I is also in that direction. However, you could have negative charges. For instance, electrons in a metal, they're moving this away, but they're negatively charged. So the current is still in the opposite direction. It's in this direction because that's the direction that I could say is positive. Why? When these minus leave, it's as if I'm leaving behind positive charges. So the positive charges that weren't there have now moved across, if you would. Now, when this was done years ago in defining positive and negative charges, they didn't actually know which charges were the ones that did motion inside, for instance, metals. It turns in most metals, at least classical ones, are electrons, is negative charges. And in some fields like electrotechnology, who mostly just deal with metals, they actually take and draw their currents as the direction of electron flow. But engineers and physicists work in a more varied amount of materials, and we define it as the direction of a positive charge would flow. So that's what I've done here. Now, given that, let's take and get the units of this current. The units of current are the amperes, or usually we shorten that and we just say they are the amp. So we usually just say amps. An amp is equal from the definition to a coulomb per second. And usually we just use the symbol A. Now it turns out that the amp is actually one of the fundamental units in the MKSA system. The MKS system is meters, kilograms, seconds, and amps. It turns out it's easier for us to measure currents. We have devices like ammeters to do that than it is to measure charge, which can leak off or be picked up. So instead of actually measuring coulombs, we actually measure amps. That's the definition, and then integrate that over time to find charge. So although we did it this way, it's not the way the unit system is set up. The next thing that we need to take a look at is some models for current in a conductor. Although you can work with wires and not understand really anything more than kind of a heuristic approach about what things going on, if you really want to understand in electronics, if you want to be an electrical engineer, you want to be a physicist, then we need to have a microscopic understanding of what is going on in current. This is very useful in troubleshooting electric circuits, and it's useful in understanding how modern devices work. So in the metals, at least, one way of microscopically treating them is to treat them by kind of what's called the Drude model, in which we treat them like they're randomly moving molecules. In other words, it's also known as the free gas model. So in a free gas, back in your physics 1, you should have seen that there are a lot of molecules inside a gas, and that those molecules are moving in all directions. This one, for instance, is going this way, and this one's going like that. That one's going like that, maybe like that, and over here, and over there, and up, and over, this way, so on and so forth. Inside the motion of the charges, a few electrons, the outer electrons, are actually shared between the various atoms. And so you can treat the nucleus and the tightly bound electrons as if they're an ion. And those ions are, except for vibration, held in place. But the electrons, the few outer so-called conduction electrons, are allowed to move around basically like they're free, being shared between the various atoms of the solid. So we can think of those electrons as going in, again, all different directions, just like they were molecules inside a gas. Now, the net motion here is 0. I didn't say they're not moving. In fact, you can calculate a root mean speed for these things, and you find that they're literally thousands of meters per second. They move a lot, but they're as equally likely to go to the right as to the left, and up as and down. And if you calculated the average velocity, you'd find that's 0, just as you would do it for a gas. So how do you get a gas to move? Well, you give a pressure to it, and that gives them a net motion, for instance, to the side, even though they're still bouncing in all directions. In the same way, we give a force pushing these guys, and we give that force to an electric field. We are going to do that by hooking it usually up to, for instance, a battery. So in the gas model, you can think about a piston providing this force. And so, yes, they're still moving in many different directions, but there's a net component in the horizontal direction that the piston is pushing. So there's a net flow in that direction, or a net drift speed, if you would. In the same way, when we put the battery, there's an electric field set up, and if these were in fact positive charges, there would be a net component pushing them in that direction, so that there'd be a net flow in this direction here. Now, even though there's a net flow, there's actually a lot more motion like this. So watching my little pulsar, little pin here, they're really doing like this. Now you put the battery on it, and they're still bouncing around, but they're moving slightly over to the right as they bounce around. The motion to the right may only be a centimeter per second, while the net motion may actually be in kilometers per second. But the kilometers per second is in a random direction, it cancels out, while this other component, due to the electric field, pushes them to the right. That's why it's called a drift velocity. It doesn't really fly across, it kind of drifts along like a boat on an ocean wave. In the next video, we'll actually go ahead and develop us a formula for calculating this drift velocity and how it is related in the metal to various properties and to the value of the current.